All right. It is officially 8:30. I want to say good morning to everyone. And please, everyone, right now, this very moment, go to WebAssign and enter 1 for question 2. You answered question 1. Already. So now please answer question 2 by just entering number 1, choosing. Because I really want to have at least one question with 100% correct answers. Let's see. Yes. No. I'll find you. At least you have an explanation. Moving on. So this is the summary of almost everything we've learned about ideal gas. And, well, this is an actual question about a specific gas which is expanding from a given volume to a new volume at a constant pressure. And the process like that has a name, isochoric process. So I prefer, at least at the beginning, specifically say that the pressure remains constant. However, a similar problem could just say in an isochoric process, the gas expands, and in that case, you should know isochoric means the pressure remains constant. And it's always helpful to draw a picture or diagram. In this situation, a picture of a gas doesn't really help because it's basically something like this. But a diagram, PV, pressure volume diagram, usually tells something important. And so what do we know? We know the initial volume is equal to 3 liters, and the final volume is equal to 7 liters. The initial pressure is equal to 300 kilopascals, and because the pressure has to remain constant, this is the initial state. This red dot represents the initial state when the gas has the volume of 3 liters and the pressure of 3 kilopascals. And when we change the state, what does change? The volume. What doesn't? The pressure. So we have to draw a horizontal line. This work is based on our knowledge of how to graph. This is this final state. And we know that in general we can talk or ask or calculate the work done by a gas and on the gas. And in this situation, the work is done by the gas. And when the gas expands, the gas always does positive work. So specifically, when pressure remains constant, to calculate work, we have to just multiply the pressure and the change in the volume. And if the final volume is greater than initial, that change will be positive. That's it. Of course, we need to calculate something. In this situation, first, we need to calculate the internal energy. There are many equations we can use. They're all provided on the equation sheet, and by now, you should have it printed out and using every time when you need to solve any problem. So you would get used to using the equation sheet. Well, the first equation, which relates the internal energy, also relates it to the temperature. And we have no information about temperature. We could get that information from the ideal gas law, but it's just easier, faster, simpler to using an equation which directly relates the internal energy, pressure, and volume. Well, we can write it twice. First time for the initial value, second time for the final value of the internal energy. But the first equation, again, represents a case when the same letter represents completely different things. For example, this subscript represents word initial, and this I represents the number of degrees of freedom, which depends on the structure of the gas. And the hydrogen is a diatomic gas, hence this number has to be equal to 5. And if we want to calculate the change, we have to subtract two numbers, final minus initial. And that's going to be 5 over 2 pressure. And I don't use any subscript for the pressure because it's the same, times final volume minus 5 over 2 pressure times the initial volume. Now we have to use our knowledge of algebra. 5, 1/2, and P represent common factors. We can pull it outside of the parentheses, and what we have in parentheses is the change in the volume. So this is an equation. It was yesterday on one of the slides for the isochoric process, which relates the change in the internal energy, pressure, and the change in the volume. And of course now we just plug in numbers into this expression. 300, well, first I do this, kilopascals times 7 minus 3 equals what? 4 what? Liters. Exactly. We cannot use technically liters, so we have to do a conversion. Kilo means 1,000, 10 to the third pascals. 4 times, and by now we probably should remember how to convert 1 liter into cubic meters because we did it yesterday and before that. It should be 10 to the certain power cubic meters. What power? -3, because we remember 1 cubic meter fits exactly 1,000 liters. And now a miracle happens. Manufactured by our own hands, 10 to the third and 10 to the -3rd getting canceled out. So turns out if we use kilopascals and liters together, we don't have to convert because the result will be the same. It's going to be 5 over 2 times 300 times 4. And it's just a time-saving technique which might save 2 seconds. But of course, you can always convert liters and kilopascals and get the same number. Now we can finish our calculation. 4 over 2 is 2. 2 times 5 is 10. 10 times 300, 3,000 joules. This is a very typical calculation for this type of problems. All right. So the work is positive. Now, same process, same gas, same process. We just need to calculate heat. So the equations on the screen do not give any equation with heat. So we start searching through the equation sheet or our memory. The first which comes to mind is Q equals Cm delta T. Well, we could have used this equation if we knew the specific heat of hydrogen. And you could Google it because it's a fixed number. But actually faster, easier, more convenient. Okay. Is just try using a different equation, the first law of thermodynamics. Because we just found the change in the internal energy. If we can find the work, we just have to add 2 numbers, done. How can we calculate work? Well, first, for the isochoric process, it is equal to this. And we know pressure, and we know change in the volume, 300 kilopascals times 4 liters, 1200 joules. Now, there is also another approach which sometimes maybe at least as quick as this one. We know that the change in the internal energy is equal to 3,000 joules. And we know that change in the internal energy is equal to I over 2 times pressure times change in the volume. But this is work. So now we have an extra relationship which connects directly work and change in the internal energy for the isochoric process only. So if pressure remains constant, these 2 variables, change in the internal energy and work, related directly by a simple proportionality. So we can use this relationship to calculate work differently. It's going to be equal to 2/5 times delta U. Two times 3 is 6. 6 times 2 is 12. 12 over 10. Of course, we get the same number. But it's also check, which tells us everything we've done before is correct. And now the amount of heat will be equal to 3,000 plus 1,200, which gives us 4,200 joules. And that is a positive number, so it absorbs heat from the, well, external. Yes? Whatever you may think, it's just what you think. Equations tells us the truth. It absorbs energy from a heat plate, for example, or from hot water. And because of that, molecules inside the gas starts moving faster and faster and faster, and they push on the piston and then pull it. And that's how they make work. That's how first steam engine worked. You burn coal or wood, boil water, aim vapor on turbine, it spins. And all that energy comes from burning something, which chemical reaction. Yes? Good question, which forces me to ask this question to everybody. First of all, the equation for work, when temperature remains constant, is just given as an example. The derivation of that equation requires calculus, so basically that's outside of our scope. But a question about work for the isochoric process is good. Constant volume. A work is a number. As any number, it can be positive, 0, or negative. So we only have 3 choices. So please tell me what you think. When the volume remains constant, the work done by the gas is. Now, if you think positive, please raise your hand. If you start raising your hand, don't switch it to, just keep going. If you think 0, please raise your hand. That's correct. When volume doesn't change, the gas doesn't do any work. You can use a graph. And this is the graph. It has no area. Or you can choose the expression for the work. In general, it equals to average pressure times change in the volume. And when there is no change in the volume, doesn't matter how high or low pressure is, there is no work. Our next example, so we have a monatomic gas, and the initial pressure and initial volume is given to us. We need to calculate the initial temperature. Okay, to practice how to use the ideal gas law. Okay, let's calculate the initial temperature and enter your choice. Again, you should choose the equation you want to use. First you choose, then you use. And using an equation means plugging in that equation, all the values given to you, and then you take in a calculator and carrying out the calculation. And you can see only 3 possible choices, but your powerful pattern recognition device, brain, tells you that if your answer would be equal to 400 Kelvin, you would have to choose number 4 answer. For our convenience, we don't given the number of moles directly. We already know the product of n times the constant, n times r, is 20. Of course, 20 over 8.31 tells us the number of moles, if we wanted to know that. But we don't have to. It's interesting to look at the units of the ideal gas law. On the left, we have joules. Pressure times volume, joules. We just used a similar expression for calculating work. But on the right, we have kelvins, and, well, everything works out, because if you remember, an official definition of temperature is just, it's a measure of average kinetic energy. So temperature technically is energy, just in a weird unit, Kelvin. So let's see how many answers do we have already. And that's the question number 4. And I think number 4, and I think it's supposed to be 100. So, of course, we need to relate pressure, volume, temperature. So it forces us to try using the ideal gas law. And 20 kilopascals times 100 liters should be equal to, this product is 20 times the initial temperature. And as we know, we don't even have to convert kilopascals and liters if we keep them together. So it's 20 times 100 over 20, 100 Kelvin. So next question, now, if we start, I cannot hear myself. Can you hear me? My microphone tells me bye, literally. By the time I change the battery, you should already have solved this particular problem. All right, we are back. So now we are adding some heat to this gas, and it expands at constant pressure and has a new equilibrium state, and we need to calculate the new temperature. Okay. Oops. I have a question to you. I would say definitely not need to use. We sure assurances, yeah, you know. to solve this problem, to answer this question, to calculate the final temperature, we're definitely not using, and pick one. So if you have any doubt about using or not using specific equation, you don't pick that equation because it might be used, but there's at least one which you would definitely not need to use. So which one is that? Pick one from the list. And we know that the amount of heat and temperature are related, and the relationship we used to use looks like this. However, again, it's not useful. It's not even on a list right now because we don't know properties of this particular gas. We don't know specific heat, so we have to use for different connections. The amount of heat is related to change in the internal energy and work, and change in the internal energy and work related to pressure, volume, and temperature. So this map of connections gives us an idea what should we try to use. So we have to try to use first the first law of thermodynamics. That's the only another equation with Q, with heat. And then we would have to try using probably these two equations because they related to temperature. So that's an idea. Now, after having an idea, we have to give it a try. So Q equals delta U plus W, which is for the monatomic gas, the number of degrees of freedom I equals 3. So 3 over 2 and R times delta T. What did I just do? I looked at the equation number 3 and I added delta to it. And I always can do that when the number of moles doesn't change. If we don't poke a hole in the container or don't adding any molecules, I is a constant, N is a constant, R is a constant, only temperature changes. Now, plus work. Work, the equation at the bottom is equal P times delta V. But if I look at the equation number 1, the ideal gas law, when the pressure remains constant, the number of moles remains constant, R is constant, I can add delta to variables which change. Only volume changes and only temperature changes. So this makes my equation look much simpler because now it has only one changing variable, delta T. Actually, I could have used 24 N times R, and I will right now. So delta T and this product N times R, common factors, so we can write them outside of the parentheses. Delta T times 20 times what's left, 3 over 2 plus 1. And that tells us how to calculate delta T, because the amount of heat is a given number, 250 joules. So now, to calculate the change in the temperature, all I have to do is divide to 2500 over 3 over 2 plus 1, 3 over 2 plus 2 over 2 is 5 over 2. So it's 20 times 5 over 2. Start crossing out zeros, 2's. 25 over 5 is 5 Kelvin. That's not the final temperature yet. That's the change from the initial to final. But the initial is 100 because we just found it a slide before. So the final temperature will be equal to the initial plus change. Hence, the final temperature will be equal to 150 Kelvin. Please ask me any question. And I mean any. Do aliens exist? Yes. You know that in an hour or so this slide will be posted on Blackboard. When we started this course, one of the advices was not trying to write down everything. Write down only things which confuse or raise a question to follow up on that later. But writing down everything just well, it makes sense because it, in one sense, it helps to excite more brain cells, more neurons, which is always good. All right. Empty slide, okay. Yeah, 150. How much work was done? Well, we actually found it just before. The work was equal to pressure times change in the volume, or the amount of gas times constant times change in temperature. That was 20. That's what we have found. Right? Ah, that was a different problem when we're here. So 1,000 joules. Right? Yeah, we didn't calculate that number for W. We didn't calculate that number for work for this problem. So we used an expression. Now we have a number. And of course, actually, we can calculate the change in the internal energy because it has to be equal to the difference between the supplied heat and the work done. And supplied heat was 2,500. The work done is 1,000. So 1,500 joules. And if you want to calculate the final volume, now you just have to apply the ideal gas law equation one more time, because we know everything now. It will be equal to 20 times 150 over what was the initial? What was well, initial and final pressure should be equal to each other because the pressure remains constant. And when I write it like this, yeah, kilopascals, the answer is automatically in liters, if you want to. Done. This calculation gives meters cubed, which is the same number with a different unit. Well, next example, very similar, I suppose. We have gas Do I want to do this? It's very similar. No. I might go back to this problem, but first I want to ask these questions. So, there are two questions for this particular situation. They don't really require a calculation. One question is about work. Second question is about change in the internal energy. And by visualizing what is happening to this gas, you should choose what do you think about work done by this gas. And what do you think about the change in internal energy of that gas? This is a more important conceptual question. So, of course, every time when we read a text, different words have different weight for us, different importance. So, for example, heat can be transferred or taken away. Now, the volume can change or not. These are clues which immediately tell us something about work. What? 0. And then, so, when volume remains constant, the work has to be equal to 0. That's it. But then, the heat, the change in internal energy, and work are related. 2 means system absorbs heat, so Q is positive, W is 0, hence delta U, which is equal to Q, is positive. But even more, delta Q, delta U, which is equal to Q equals 62,325 joules. That's it. Answered. All right. I'm going to give you a minute. So we start solving problem when information is presented using a graph representation. So this graph has 3 different processes. And 3 different states. Numbers count states. So this dot represents the state number 1. This dot represents the state number 2. This dot represents the state number 3. 3 states. And the gas changes state from 1 to 2 to 3 to 1, well, to 2 to 3. We're going to talk about it probably tomorrow. This is a cycle. And each process connects 2 states, initial and final. Each process has a direction from one state to another state. And for each process, we should be able to say what is happening to pressure, volume, and temperature, if anything. So, for example, for the process between state number 1 and state number 2, and we can call it process number 1. pressure remains constant, but the volume increases, which means temperature should also increase. For the state, for the process number 2, from the state number 2 to the state number 3, pressure changes, pressure drops, and the volume drops. And the temperature also, but we have no means so far to write an equation for temperature change, but we can calculate the temperature initial and final. Now, process number 3, from the third state to the first, is isochoric. The volume doesn't change, but the pressure increases, and the temperature should also increase. Now, the work done on the gas during process, well, we called it process number 2, from the second state to the third state. And the key word here is on. If you missed that word, your answer is opposite to the right one, because there is a difference between work done by a gas and on the gas. What is the difference? Well, remember, the work done by the gas is just opposite to the work done on the gas. That's just a representation of Newton's third law. So if I look at the process number 2, the volume decreases, hence the work done by the gas is negative, which means the work done on the gas is positive. It is us who compress the gas. That's it. So one word only, but we have to pay attention to those words. Well, probably, oh, I just did it, yeah. Probably we need to calculate something right now. It's a diatomic gas. We have to calculate work. Well, we have to calculate that work, okay. So we can use different approaches, trying to calculate average pressure and then use P times delta V, but we also can use the fact that the work done by the gas is equal to the specific area. So from 1 to 2, this is the process. If we look at this process, the volume for the process 1, 2 increases. Hence, we know the work has to be positive, the work done by the gas. And what it should be equal to? This whole area, from the bottom axis to the top line. That's the work done during this process. But now, well, all we have to do is multiply two numbers. So this work should be equal to this area, should be equal to P1 times delta V. Now I have to name, well, I have to name technically each state. So this state has P1, T1, V1. This state has values for P2, T2, V2. This state, number 3, has values P3, T3, V3. And what we need to calculate is the product of pressure number 1 and the difference between volume number 2 and volume number 3. But if we look at the graph, state number 1 and state number 3 have the same volume. So and the pressure number 1 and the pressure number 2 has the same value. So I can just start plugging in numbers. 600 kilopascals times the volume number 2, 120, minus the volume number 3 is equal to the volume number 1, 40. So, and those are liters. So I can cancel kilopascals in liters. 600 times 80, 48,000 joules. Now I want to write immediately that the work done during process from state number 3 to state number 1 is 0. And what would we do about work done during process from state number 2 to state number 3? We would have to calculate a different area, the area of this trapezoid, of this shape. And that has to be, the work done by the gas in this situation has to be negative. So this is how we should write it so we wouldn't make a mistake. The minus 1 times the absolute value of this area. How do we calculate area? Well, it's a trapezoid. You can use the equation for area of a trapezoid, or you can break it into two different figures, a rectangle and a triangle, and do that. Does it change anything? Technically, you're right. I just used that fact, yeah, that they equal to each other in my mind. But technically, you are correct. Because the process begins at the state number 1. Correct. By the way, looking forward, we can calculate the total work done over this cycle. We just have to add 3 numbers. The work done for the first process, second, third. We will do an example like that in the future, but that's how it was done. Okay, so the same gas, and now we have to calculate just everything. All right. But I'm not going to do everything, just something, because what can we calculate? That's the first question. What does this mean, everything? Well, for each state, we have 3 variables. Some of these are given, so for each state, we can calculate the unknown one. For each process, we also have 3 variables. And we need to understand the difference between variables describing a state and variables describing a process, because we cannot calculate work at the state. State has to change. So we have 2 sets of variables. And of course, if we have three states times three variables, 3 times 3 is 9. And we have three processes and three variables, 3 times 3 is 9, and 9 plus 9 is 18. Technically, we can calculate 18 different numbers. Well, some of those are given. 1, 2, 3, 4, 5. So the rest is possible. So we know P1, V1, we can calculate T1, for example. If we want to calculate T1, we should use the ideal gas law. It should be equal to P1 V1 over N times R. That's a very quick calculation. 600 kilopascals times 40 liters divided by 300, the number given to us. So that results in 0.0002, 2 times 4, 80 Kelvin. Now, G2 should be equal to P2 V2 over NR. If we look at the list of pressure, 2 is not given, but if we look at the graph, it has to be equal to P1 because that line represents the isobaric process, sorry. And that again gives us 600 times new volume over 300. So that's going to be 80 times 3. Now, delta U, for example, for the process 1, 2. It should be equal to I over 2 and R delta T, or I over 2 P delta V. In this situation, it actually doesn't matter. We know both. Yeah? So, or it can be equal to I over 2 times W. Because it's a diatomic gas, divided by 2 times the work we have found, which was equal to 48,000. Joules. Now this graph represents a specific situation when there is one tricky moment. So I want to show it. Don't expect anything like that on a WebAssign. But if we look at the process number 2, from state number 2 to state number 3, this line doesn't represent any standard process, not isochoric, not isobaric, not isothermal. So we cannot apply any specific physical equation. However, we can apply mathematical equation because this line goes straight to the zero, to the origin. So we can just relate these variables purely geometrically. That's a straight line. If you want to calculate this slope, we could do this rise over run. So P2 over V2, and the same slope should be equal to P3 over V3. And how can we use that? Probably, okay, so let's see what we can calculate from this. P2 and P1 are equal to each other, P3 is given, V1 is given, I think actually we, let me check. P1 and P2, 1, 2 equals, so 600 over 600 over V2. And here, maybe we have an extra variable known. And P3 is 200 over V3. So the third volume and the first volume should be equal to each other, which is 40. It is equal 5, right? 0, 0 canceled, 5, 0, 0 canceled, 5. So what we could have done, we could have erased one of these variables and find it from this relationship. So someone, I don't know who, made our life easier. Okay, that was just an illustration that sometimes the graph tells more than physics. But of course, if we know everything, we can calculate everything. We just have to apply exactly the same equations again and again and again and again. So I'm not going to do that. Now, this is the same demonstration you saw yesterday. I have now, if I can stand it, it's not too hard. I have a device which can do work. Well, it's empty. Well, because I finished it. So if I squeeze it, my hand does work on the gas, and the gas now here does work on the piston, lifts the car. And instead of squeezing it, I could burn coal or oil. In my example, it's just a hot water. And if I place it in hot water and wait, the gas again does work. But the problem is if it does it only once. Well, it moves slowly. Yeah. So if I want to repeat the same work again and again and again, I have to bring the system into original state. And how can I do that? I have to use a cooler. I have to cool it down. And when it is brought to the original state, now I can again put it in a hot water, and now it starts doing positive work again. So twice. So now I can repeat the same. I can bring it back to the original state by cooling down, taking heat out, and again, and again, and again, and again. And in that case, I can make it work for me for a long period of time. That's what we call an engine. An engine is a device which does mechanical work using heat energy. And just a second. What is the last question which has been answered? Let me check. By the way, yesterday I gave an assignment to some lady to ask me a question today. Who was that? Yesterday she approached me and asked me a question. Is the final accumulative? And I asked her to repeat this question today. Well, probably. Well, are you here? All right, so also I had a similar question in an email. I just refer to the syllabus. That's what the syllabus says. The final formally is not accumulative, but physics is. You cannot erase from your memory everything you learned before. It might be useful. But there is also another matter we have to take care of. Please, Ms. Baum, don't mess it up, please, this time. Everybody, question number 9. Please enter number 5. I'll find you. Well, anyway, there is an official procedure which has to be taken care of. And now everybody should receive an email. Please check your email. Bless you. This is the copy of that email, just in case. And I do it, it's my tradition, I do it 2 days before the exam, course evaluation. Every time before this year, you had to do it using paper form. This year, as an experiment, you have to do it online. So please go to that link for your convenience. You can just click on the link in your email. And you should follow the instructions. So you should enter your Kerberos name and password. And probably the most important part, there is no submit button. So as long as you answer something, it's stored in the memory. And after that, you're done. And I am done for now because officially I cannot be present during the evaluation. So I go to my office hours and I'll be waiting for anybody who has any questions. You have to use your device. A phone, a tablet, or a computer has to be used to do the evaluation online. So I'm going to give you a minute, just in case, to copy the link. That's the only information you need for that evaluation. But if you have received an email, you can just click on the link. What are we going to do tomorrow? We have to finish this topic. It's going to take maybe 20 more minutes, and then I will answer your questions if you will have them. If you will not have any questions, now I'm going to start PY106. You don't need it anymore. I'm really not sure why should I leave, but rules are rules. Oh, I can telepathically affect your actions.
in bed by 10:30. I'm like, what is happening to me? But you see, I can't